Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, it's a Tuesday in August. That means it's still IEC month. So this month we're covering 5 IEC topics. We're on our 4th today and the 2nd to cover structured text. So today's specific topic is math instructions as they relate to structured text. So again, we've talked about structured text in this channel. We've had several structured text videos. It's a really important topic. To talk about some of the advantages and disadvantages of structured text, let's bring in our product manager, Mr. Casey Gardner. How are we doing today, Casey?
Hey, not too bad. How's it going, Chuck?
Good. Yeah, structured text is definitely one of the most popular IEC languages. Why do you think that is? What do you think is one of the big positives to structured text?
I think kind of overall some of the simplicity, and especially I know a lot of the younger generation coming out of college right now is where it's emphasized probably the most. So especially for very repetitive actions, it's got real bright spots to it, and being able to handle those really easily. Those are probably some of the few off the top of my head.
Yeah, I could see for those young folks that, they're used to, Python and C and those languages where they're a little more comfortable starting out with structured text than something like ladder, which is probably pretty foreign to them. Well, there is no free lunch though, right? So no language is perfect. So what would you say would be a disadvantage to structured text?
Sure. I would say troubleshooting in general. I mean, this kind of goes for all coding for that matter, but I mean, without proper commenting or a more familiarity of whatever type of text flavor it is in that respect, could make it a lot more difficult in that regard.
Yeah, no, I would say for sure that troubleshooting can be an issue with structured text. For one reason is that on the factory floor, you often have electricians and technicians that don't have that programming background. And so when they look at structured text, their eyes could start spinning in some cases. But another thing I've heard is that with some of the structured text tools, you don't get the best troubleshooting tools within the structured text. Some are better than others. And I have also heard that the debugging, especially the ability to see live variable values within your structured text code in the Cscape IEC editor, I've heard that's pretty good. So we're going to demonstrate that later today. Okay, thanks, Casey. Now, while Casey is standing by to answer any questions you may have for those of you watching live, he'll be answering those questions in the chat section. For those of you watching on replay, give us those comments and questions in the comment section, and we'll reply to those just as soon as we can. All right, let's take a look at how we're breaking down today's topic. So we're going to start by creating a list or showing you a list of the mathematical operators, a lot of which we're very familiar with in all the different IEC languages. We're also going to talk about some of the more, in-depth or complex mathematical functions, one that you don't always think about when you're thinking about industrial control, but they absolutely do have applications there. Of course, we need to talk about data type conversion because when you're doing calculations in a PLC, you need to make sure that your data types all match to the point where, you can accomplish what you're looking to accomplish. Another thing we need to keep in mind is the order of precedence or mathematical hierarchy, not only among the operators and the functions for math, but also as they relate to other functions in the PLC. So I'm going to show you kind of a detailed chart with the order of precedence so you can keep that in mind as well. And then we've got a couple of examples to show you and of course demonstrations throughout. Let's take a look at how we get started, and we'll start with mathematical operators. Okay, so the first few of course are the ones we're going to use a majority of the time, the simple ones, right? Add, subtract, multiply, and divide. There's plenty of calculations we need to make in any control language, and structured text is no different. And one of the advantages of structured text is you can create kind of a very verbose looking algorithm made up of those various operators. So you can, instead of having to have 4 or 5 different calculations, you might be able to put it all in one line of code, for instance. And if you use spacing and parentheses effectively, you can end up with a pretty readable result as well. Well, in addition to the add, subtract, multiply, and divide, we have some other ones we need to keep in mind. One that we don't think about that much that I've used many times in programming, and that is modulo. What is modulo used for? Well, I've got an example of the syntax shown there on the screen. But effectively, modulo is used anytime you're interested in a remainder. So you're going to take a starting value, you're going to divide it by a second operand, and then whatever the remainder is after that division, that result is your modulo. So there's plenty of applications where that can be useful. Absolute value. In some cases, you really don't care about whether a result of a calculation is positive or negative. You're just interested in knowing the magnitude of that. How far away from zero is it? So absolute value, of course, is the way we can calculate that. And of course, there's exponents and square roots, all available as our basic arithmetic operators. Now, if we take a look at the syntax with structured text, I've got several examples here on the screen, some just using the normal addition, multiplication, etc., some using some functions like modulo and absolute value. And in general, what you're going to have is the result is going to be placed in the variable on the left. So in every case, in every example, I've named that resulting variable result. Now, the operator that you use there, you can see the colon equal sign. So it's always very important that you don't forget to use that assignment operation. That's what that's called, an assignment. So you use the equal sign alone if you're testing a value. You know, if this variable equals that, then you would use the equal sign alone. But if you're assigning a value or assigning a result, then you're going to use the assignment operator, which is colon equal sign. Another example you can see there at the bottom, I'm showing you raising, there in that last example, I'm showing you taking a variable called variable n and raising it to a power, and that power I'm raising it to is stored in the variable exponent. So just some examples there on the screen I thought would be useful for you to see. Okay, now let's dive into some of the, I guess, lesser used but highly useful functions. We're going to start with trigonometric functions. And trigonometric functions are named because they're really all about triangles. The TRI in trigonometric and the TRI in triangles. And of course, the ones we're going to use most often in general are going to be sine, cosine, and tangent. You can see the definition of those as it relates to that triangle diagram there on the screen. And a little bit later on, I'm actually going to show you how you might use tangent as an example to calculate an important piece of information in a control application. So we're going to show you a specific example based on tangent, but all of these different trigonometric functions do have application in industrial applications. Okay, now let's talk a little bit about the units that we need to use when we're doing trigonometric calculations. And that is, we need to use radians. So in most PLCs, and the OCS is no different in its structured text editor, when we're doing trigonometric calculations, whether it's structured text or ladder or whatever the language, we're going to be assuming, or the OCS logic engine is going to be assuming, that we're using radians as our units. So if you've got an application where you're starting with degrees or you need to end up with degrees, then there are conversion functions that can be used to convert from degrees to radians or vice versa. So keep that in mind. You've got those functions available to you to make sure that you keep that straight. Okay, now let's talk a little bit about logarithmic functions, which, yes, are available, starting with base 10. So what are logarithms good for? Well, base 10 logarithms are great if you've got, let's say you've got an application where you're sampling a specific sensor or something, and your results have just great differences in magnitude. You know, you might have some results, that are 10,000 and above, and other results that are just a few units. Whenever you're comparing data that has a great difference in value, sometimes comparing them on a logarithmic scale can be very useful. So how does that work exactly? Well, what a logarithm will tell you, what a base 10 logarithm will tell you, is how many orders of magnitude is a certain value away from 1. So let's say we're going to take the log of 1,000. So the 10 base log of 1,000. How far in orders of magnitudes, how many 10 times steps is it going to take to get from 1 to 1,000? Well, one step's going to get us from 1 to 10. The next step is going to get us from 10 to 100. And the third step is going to get us from 100 to 1,000. So the log of the 10 base log of 1,000, the answer of that is 3. So whenever you scale things logarithmically, you can take some really large values and make them easier for people to kind of comprehend as you compare it with some smaller values. So that's something to keep in mind, a very useful function when it comes to log base 10. Now, natural logs are another logarithmic calculation that can be made in the OCS, and those are really best for analyzing growth. Okay, the growth of numbers, whether that's, the growth of a sample in some sort of, bacterial application or something else. But basically, we're talking about growth there. So let's start with, for instance, the fact that when we're talking trigonometry and we're talking triangles and circles, there's a constant we use all the time, right? That is pi. The pi r squared is the area of a circle. 2 pi r is the circumference of a circle, those sorts of things. And we use pi in triangles as well. But when we're talking about natural logs, we're talking about another constant, and that one is e, where that does not have a value of 3.14. It has a value of 2.718. Okay, so that's a constant that we use as we're analyzing growth. Now, if you're going to do an e to the x calculation, what is that all about? Well, the best explanation I found for that is this. So when you're calculating e to the x, the result effectively is the value that you would get if you started with a value of 1 and you were growing continuously over x units of time, the result would be e to the x. And in reverse of that, or the inverse of that, if you know the value you grew to, and you want to try and figure out how long it took you to get there, if you started from 1, then you can take the natural log calculation. So again, when you're talking about growth over time, whether you're trying to calculate the growth value or the time value, that's where natural logs can be useful. And yes, you can use PLCs, including the Horner OCS, and you can use these functions in structured text. They're also available in the other languages as well. Okay, now let's talk about some which are probably a little more obvious as to how we can use. Now, of course, we can use add, subtract, multiply, divide for doing things like linearization. How do we use linearization in industrial applications? Well, scaling analog values is the most obvious application for that. So, of course, you can use, y equals mx plus b scaling, and we'll show you an example of how to do that. But there also are some specific purpose scale functions available for you to use. So there's an integer scale function, and there's a real value scale function. And I've got the syntax for those shown on the screen. They're very easy to use, and we're going to demonstrate one of those for you a little bit later. Now let's not forget to talk about data type conversion, because if we're doing calculations, it's very often that we're going to start with an integer value, or we need to finish with an integer value, but we are doing calculations that maybe we want to do in floating point. So in that scenario, we need to do conversions very often from integer to real, or vice versa are two of the most common. So in structured text, you've got a full array of functions for converting one data type to another. Okay, now let's talk a little bit about arithmetic hierarchy, or the order of precedence. And I've included more than just arithmetic functions here. From top to bottom, we're showing in priority the precedence of the different operators, starting with the parentheses as well as the absolute value at the top of the food chain. I was a little surprised in kind of reviewing this. I'd kind of forgotten that you consider absolute value just like, it's almost like another bracket type function. So it's at the top of the food chain there, and you can work your way down, through the functions, negations, exponents, etc. So we're not going to spend too much time on this chart. For those of you watching on replay, you can freeze frame it if you choose and take a look at it in more detail. But it's always important to keep in mind the precedence in your application so you end up with the result you're looking for. Let's do a demonstration now showing you how to use structured text to linearize some analog values. And we're going to show you a couple of different approaches. All right, let's go ahead and fire up Cscape here. All right, and sure enough, I've got my application here written in structured text. Now, of course, one of the beauties of IEC is that you can mix and match multiple languages. For my example here, I'm strictly using structured text. Okay, so I've got this linearized routine here. And our first example, we're actually just going to use, traditional multiplication and subtraction and addition to linearize an analog value to an engineering unit. So what we have here is we've got a sensor, which is a 4 to 20 milliamp pressure sensor. So its range is 4 to 20 milliamp for its output signal, and its range in engineering units is 10 to 100 pounds per square inch. Now, when we effectively digitize this 4 to 20 milliamp signal in the OCS analog input, we are going to be converting it to a decimal value between 0 and 32,000 counts. So effectively what we're doing is converting between 0 and 32,000 and 10 to 100 PSI in this example, okay? All right, so also we have to keep in mind that the analog value coming in is an integer value. So we need to use one of those conversion functions. So we can take our analog input integer and convert that to a value or a variable that's in real format, because that's what we need to use for the bulk of our calculation. That's what I'm going to be using for the bulk of our calculation if I want my result to be a floating point value. Okay, and then here is our calculation that we're making the old-fashioned way. All right, so we're taking our raw analog value, which is going to be somewhere between 0 and 32,000 counts. We're going to be dividing that by full scale. Now, what is full scale? Well, it's effectively 32,000 minus our minimum value, which is 0. Okay, so our current value divided by full scale. And then we're going to multiply that by the full scale or the slope of the pressure curve here, which is max minus min, or 100 minus 10, which is, of course, 90. And then we're going to add to it the minimum pressure value. So if we start out with a value of 0 here, okay, we're going to end up with 10 as our result. If we go all the way to a full scale of 32,000, we're going to end up with 100 as our result. So that's what we want to have happen. So let's just take a quick look at that on the bench. Obviously, this is pretty straightforward here. So you can see on the left, I've got my pressure sensor value, which is a value between 0 and 32,000. That's at the upper left. And directly below that is the converted pressure in PSI. So I can adjust my analog simulator here. As you can see, the analog input going up and down, and you can see the resulting engineering units going up and down as well. So just a simple calculation done the old-fashioned way using mathematical operators there for our first linearization example. All right, let's head back to Cscape now. And let's take a look at doing a slightly different way. Oh, one other thing before I wrap this up. Now, with my example, I want to make sure that I don't end up with under range values, okay? Because with some sensors, you can get below 4 milliamps, and it could represent the fact that you've got, you know, really an invalid value coming in below 4 milliamps. In some cases, it's just slightly under range and you want to use it in the math calculation. In other cases, you want to make sure you don't have that result. So what I did in this example is it's possible for my result to be effectively below 10. 10 is my minimum reading. Based on if my value is below 4 milliamps coming in, just by a little bit, I'm going to go below 10 or dip below 10. So I've got added a little bit of extra code here, just a simple if-then statement that effectively says if my result is less than 10 pounds per square inch, I'm just going to keep it at minimum there, just to indicate that we ended up at a value that is at the minimum value. We don't want to go below that. Okay, so that was our first example. Let's take a look at our second example. This one, we're going to actually use a function called scale real. Okay, so this is a very useful function that's included in the math choices in structured text. And so what we're doing here is similar to before, but it's a little bit easier. So yes, we're converting our analog input value to real. We have to do that to start with. And then what we're doing with our scale real function is our input is our real value that's been converted from our analog input. That's the first listing here. And then we have the minimum value coming in, which is 0. The maximum value coming in, which is 32,000. I just made those constants. They could also be variables, of course. Minimum value going out is 0 and maximum going out is 1. Why am I using those? Well, in this scenario, we're converting from 4 to 20 milliamps to 0 to 1 meter. So this would be like a level sensor or something of that nature. And just like before, I've just got a simple if-then statement here at the bottom to filter out everything, all the values below 0 meters, because I don't want to have a negative distance there. All right, so let's head back to our bench and take a look at what things look like here. Okay, so this time I'm going to be looking at our second pot, and you can see there on the level sensor at the top right there, you can see its value is 0. That's because I'm feeding it from my simulator a value that's almost at 0 milliamps. So until I start raising that value up to the point where we get above 0, you're not going to see a result that is scaled because of that if-then loop that if-then loop that, or not loop, if-then statement I put in. Okay, but as my value increments, you can see my scaling is getting up towards 1 meter. Okay, so that's, again, simple scaling using this time the scale real function. There's also a scale integer function that you can use. And it's definitely one of the more popular ones in structured text, at least from a math standpoint. Okay, let's head back to Cscape. Actually, let's do this. Let's go back to our presentation and let's take a look at what our next demonstration is. Okay, so we've shown you some linearization examples using just standard math as well as the scale real function. Now I'm going to show you an application where you could actually use trigonometry for an actual application. So what we're doing in this example, and I've got a diagram for you here in the screen, is we have, let's say, a water jet. Now we're going to assume that this water jet has enough power that it can effectively shoot water in a straight line, okay? That it's got appropriate power and appropriate pressure. Okay, so we've got a nozzle here that we have the ability to incline up from flat all the way up to, say, 10% or so. And based on the incline angle, our water jet is going to shoot off, of course, at a different angle. Now, the point at which that end of that water jet hits its target, that's what we don't know and what we want to calculate. That's our target height. Now, the reason we can calculate this using trigonometry is because of this. We're going to be measuring our incline angle using an inclinometer, okay, and those are available from companies like Turk and others. We're going to have a known measured distance between our water jet nozzle and our target, which we're going to say in this example is 20 meters. And because we know the angle and we know the distance to the target, we can use trigonometry to calculate the height at which the water jet is going to strike our target. So the way we're going to do that is using tangent. So the tangent of an angle is opposite over adjacent. So in the case of our example, our adjacent distance of the triangle is fixed at 20 meters. And our opposite side is the target height we're trying to measure, or actually trying to calculate. So if we solve for target height, we can see that we can just take the tangent of our incline angle that we're measuring, multiply by 20 meters, and the result is going to be the target height in meters. Okay, so that's what we're going to do in our second example for structured text. Okay, so I'm going to move down here to the trig routine that I've got, and I'll show you this, and it's really very simple. The first thing we need to do is we have to keep in mind, well, okay, let's back up one step. In the linearization section, okay, I do have the linearization code very similar to what we did with our last linearization example, in that I'm using the scale real function to take the inclinometer output, which is 0 to 5 volts, almost 0.1 volts to 4.9 volts is what's coming out of the inclinometer. That is scaled between -10 and +10 degrees. Okay, so we're using the scale real function to accomplish that. Keep in mind, this is 0 to 5 volts, and our analog input in this case is 0 to 10 volts. So that's why you'll see these numbers as they are, because 10% of full scale is 10% of 3200 or 320. 4.9 volts, if you look at that count, it's going to represent 10% less than 16,000, which is midway through a 0 to 10 volt scale. And then -10 is the value at minimum output, and 10 is the value at maximum output. Okay, so we're using that scale real function to give us the result in degrees for the inclinometer. And then we've got a couple more of these if-then statements here to filter out values that are above 10 degrees and to filter out values that are below 10 degrees, because those are the only valid numbers we should be getting from the inclinometer. Okay, so now that we have the degrees, we know that theta, if you will, now we can use trigonometry to solve for the target height. And we have to convert first from degrees to radians, because all trigonometric calculations are done in radians. So we're starting with our real value of our incline that we just calculated or linearized. The result is our incline in radians. And then we're doing our calculation we just described. The jet height, the water jet height, or the target height, is going to be 20 meters, or 20, times the tangent of the angle that we're measuring with our inclinometer. All right, so let's take a look at what's happening on the bench. And let's move over to the next screen. Okay, and as I'm incrementing the simulated value from the inclinometer, and as soon as my spray angle gets above 0, you can see my target height there, or the height of my water jet, is incrementing up to maximum. So in this particular case, when we're 20 meters from target, the height of my water jet in this example application can range as low as, 0 all the way up to looks like about 3.5 meters in this case. Now, another thing we might want to do in this application, but solved differently, is we might have a known target height that we want our jet to hit, and we may have a known distance to target, say 20 meters, or I'm sorry, we may want to solve for the angle, for instance. So we might want to do this sort of calculation, but instead of solving for height, we might want to solve for angle. So, and the inverse tangent calculations are available as well. All right, so this is just an example where you could use trigonometry in your application, and of course use structured text to execute the trigonometry. Okay, so let's go ahead, wrap up our topic for today. So structured text, as we discussed with Casey, very popular language, especially since it's similar to text-based computer languages that a lot of folks coming out of college are familiar with. Structured text is great with loops. It's great for searches and finds. It's great for math. It does that very well. And there's a number of real-world applications where advanced math functions can be pretty useful. And of course, we know already that there's an infinite number of applications where just the basic math functions are useful. Okay, so this is the part of our program where I remind you that we are here every Tuesday at 2 o'clock, whether we're fully live like today or whether we are pre-recorded and streaming live with someone standing by to answer your questions. So join us here every Tuesday that you can, or watch our videos on replay. Now, I want to point out a fun podcast that myself and Bill Rainier, one of my colleagues from California, Bill runs Open Apps, which is one of the premier Horner systems integrators on the West Coast. And Bill and I joined a couple of gentlemen who have a really entertaining manufacturing-themed podcast. That's Dave and Vlad. And that was something that we recorded a couple weeks ago, and you can see the replay on our YouTube channel. So I'd encourage you to check that out. It was a lot of fun. Also, we've got a new video series that we started a while back, and that's called Making a Case for Horner. So this was a series that me and several of my colleagues did, talking about different Horner applications. It's a fun series. We've got several different topics within the series, effectively covering different industries and where Horner products have been used. So definitely check that out. I got to give a shout out to Emily Tedder for that video series. She's done a ton of work, both editing and getting things ready for the web. So way to go, Emily. All right, we still have a little bit of time left to sign up for IEC training. If you're interested in the factory course coming up September 13th and 14th, go to that link there. You can see on the screen to sign up for that. And next week, we're going to be demystifying the enhanced IEC editor. There's some confusion over standard IEC versus enhanced IEC. And really, that's more of a Horner term where we talk about some of the enhancements that we've made in Cscape for some specific capabilities that are available optionally for IEC. So you won't want to miss that as we cover that next week. If you haven't done so already, don't hesitate to subscribe to our channel. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so thanks for joining us this week. And until next week, let's all get out there and do us some good.